inverse trig functions. Here I'm just reminding you that cosine represents the length and the sine represents the height. So your job is to review at home the circle. What is cosine of pi over 3, pi over 6, sine, and so on. I know you guys don't like it. Just do it, review it once, and you should be fine. And have some cheat sheet in front of you. From time to time, look at it, and that's how you learn more. That's how I learn. Look at this. They actually can be more interesting than what usually we show you in schools. Many different waves, and they, approximate sounds recordings and so on, which sound is quieter and which one is noisier, and that's how you detect where the noise is, and you can delete the noise. Later I will teach you how we're doing it, and especially in calculus 2 we're going to show you that when you, again, recording some kind of noise of the bird in the nature, there's a lot of background noise, a river, water, or some leaves and a wind. That's what you don't want to have in your record. Sine and cosine, like in this animation, show you to detect which small amplitude will be belonging to some kind of sine and cosine. That's a noise. You delete it using inverse functions. Well, a little bit complicated than this. And that's how your recording becomes more clear. Now, cool animations I showed you before. I think this one already showed you. You can check everything in my notes. Nope. Too slow. Okay. And these guys I showed you already. But I told you before, sine and cosine, like look at the sine and cosine, they don't pass horizontal line test. So they're not supposed to have inverse. So how can we teach you that there is arcsine or sine minus 1? There is arccosine or cosine minus 1. There is arctangent or tangent minus 1. Arcsecant. How come? They don't even pass horizontal line test. That's why we're going to teach you in this chapter that inverse functions help us. They tell us, okay, they did not pass the horizontal line test, but we can have the inverse on the restricted domain. We had this before with y equals x squared. Parabola doesn't pass horizontal line test, but when we're restricting it from 0 to infinity or minus infinity to 0, we can do it. And here's a picture. You don't have to copy it exactly right now. You can do a little nice picture later at home or print the card. But when I'm having only this piece for sine, here it is. You see, I'm not keep going. So I'm just cutting it from minus pi over 2 to pi over 2, so the domain will be restricted. Range is always from minus 1 to 1, because sine and cosine are jumping from minus 1 to 1, unless there's a squeeze or shrink. Now, then I can use the inverse functions. How do we build inverse function? Graphically, who remembers? Something about the mirror. Remember? There's a mirror. Reflecting upon what? Y equals x. Good job. Y equals x uses as a mirror, and that's why it kind of looks almost the same, but it's not. Everywhere where sine was going to be going down, arcsine is going up, and so on. So this is arcsine. Do you know that arcsine and sine minus 1 is the same thing? Sine minus 1 is not 1 over sine. Sine minus 1 is notation of arcsine. I usually write sine minus 1 because it's faster to write than arcsine, but I usually call it arcsine because it's only one English word versus sine minus 1. So for a foreigner, I kind of like it more. But you should know it's the same thing. Cosine, same idea. I just cutted it. I cutted it in this case from 0 to pi. So domain now is from 0 to pi. Then I used the line and created arccosine, which is cosine minus 1. See that the domain becomes range and the range becomes domain. If my cosine and sine used to be from minus 1 to 1 on the range, on the output, then domain for the arccosine and arcsine will be from minus 1 to 1. Same with tangent and arctangent. Do you remember that tangent has tons of vertical asymptotes at negative pi over 2 and pi over 2? Tangent is keep repeating itself. Do you remember that? It's like one more and then one more and then one more everywhere, right? So we're just ignoring all those other guys. We're like, whatever. Just keep one, and then you can always jump to another ones if you want. From minus pi to pi over 2 to pi over 2. Those are vertical asymptotes over here. So, since tangent had vertical asymptotes, what do you think gonna happen with those asymptotes for arctangent? They become horizontal, good job, at minus pi by 2 over here, and so on. And domain, so range for the tangent used to be infinite, then domain for the arctangent will be infinite as well. We need you to remember this. But actually not all of it. The last two functions will be important for calculus 2 class. For calculus 1 class, it's enough to have, okay, fine, don't like it. It's enough to have these four. And these four are actually couples. Arcsine and arccosine, arctangent and arccotangent. The last two with the absolute value, guys, look scary, but we will need them at the beginning of the calculus 2 class. So just to let you know, it will be important. How did I remember this? I have bad memory. That's why I chose mathematics, partially because it doesn't require me to memorize a lot of things. Many of them are logical and I could just derive them. This, I had to memorize this, so how did I do that? I will show you how we actually get these functions, but somehow it doesn't help you to memorize it. I don't know. I remember that both arcsine and arccosine have a square root in the denominator. That's what I remember, both of them. But just like sine is positive and cosine is negative when you differentiate them, arcsine and arccosine have the same thing. Arcsine derivative is positive, arccosine derivative is negative. So that's already makes sense. It matches with my previous knowledge. And then I remembered that it should be 1 minus input squared. And this is how I will be referring it to. 1 over a square root 1 minus input squared. In calculus 2, we will be calling it u squared because we're going to have u substitution. That will be better if you remember it as input squared, because we're not going to give you arcsine of x. We're going to give you arcsine of 75x squared over 5. And you have to figure that out. So I will show you the example right now. So remember, they are the same, but one is positive, the other one is negative. Arctangent, I remember, has no square roots and it's positive in a denominator. And it is 1 over 1 plus input squared. Arccotangent derivative is the same thing, but with negative sign. So this is what we need you to memorize. The other two don't have to. Not too bad. I don't know, it looks scary. I think the first time you look at it, you're just like, when this gonna be over? But I'm telling you, you get better at this the more you use it. And of course, we're gonna accumulate many formulas for you to become scientists at some point, to join the lab, and you're good at this. You're just good at this. You know what they're talking about. They say, don't you see the square root? Oh, that's used to be a derivative of arcsine. And you're like, yes, I know what they're talking about. Let's practice. Examples. 1. So, taking this idea, can you differentiate? I will do y equals 7 arcsine, sine minus 1, of x to the 4. You see, I did not give you arcsine of x. That's just lame to give example like that. We immediately want to check that you understand chain rule and how the formula works. That's why you should not remember these formulas as 1 over square root 1 minus x squared. Memorize it as input squared. Input squared. I promise you, you will have less mistakes this way. It will be easier if you do input squared in your mind. So let's see. The formula says, like I told you, this is how I memorized it. Arcsine, so it's not negative, that's good. I remember it was a huge fraction, 1 over a huge square root. And it starts with 1 minus. That's like the picture I see in my mind. That's the derivative of arcsine. Okay, there's a 7 in front just because the example has 7 in front of it. And now I remember in my mind it was input squared, not x squared. Input squared. That's a big difference because what's my input? X to the 4, right? So if you just remember x squared, you'll write down x squared and it's wrong. You need to have in your mind input squared. So I have x to the 4, guess what? Squared. And that's important. Is this the end? What else? Derivative of the function inside, exactly. Chain rule. Chain rule says, I think you never differentiated x to the 4. And that's how you should know that you missed something. Because if I give you x to the 4 and I ask to differentiate, probably at some point you were supposed to differentiate x to the 4. Make sense? So if you forgot, that's what you lost. You lost the chain rule. Times, and I usually put it in the numerator right away. What is that? Derivative of the function inside, 4x cubed. So the simplified version will be 7 times 4, which is 28, x cubed all over this huge square root. 1 minus x to the 8 or 6. Which one? 8. When you remember this, let me finish. Y prime equals. Remember that if you have x raised to the 5, no, I'll do actually this way. A raised to the x, and then raised to the y, and then raised to the z, and then raised to the t, whatever, it becomes a x times y times z, versus a times x, to the x, times a to the y times a, what's going on? A to the z, then you add them, x plus y plus z. Power to the power to the power, they all multiply. So see my lecture 0, the review lecture I give. Not too bad. One more. Not too bad if you're careful and don't freak out too much on the exam, for example. One more with arc cosine and log at the same time. Oh yes, now you can imagine we're making this interesting. Arc cosine have double C over there. Arc cosine of a to the x. Arc cosine of a to the x. Okay, you have your cheat sheet in front of you. I do recommend you to make a cheat sheet. I have it. It looks like this. Looks like this. Just a table with those formulas. I have it. And then you look at it when you do your homework, and at some point you memorize it. So I never sat down and just memorize it. It's just, if you do it 25 times, at some point you realize it's too boring to take the piece of paper and look at it. Now you know it. So it's just easier this way. So arc cosine, I just introduced it to you, so I don't expect you remember, but this is how I remember it. I remember there's like 1 over and then a huge square root, 1 minus. But since sine gives you positive, and arc sine gives you positive when you differentiate, same with cosine. Cosine gives you negative, so arc cosine is negative. 1, a huge square root, 1 minus, and then in my mind, I keep it input squared, remember? Input squared. What is my input? 8 to the x. And this is squared. Make sense? Am I done or not? I never differentiated a to the x, so that gives me a hint something is missing. So do times, and now I finally show you how I do it. I put negative sign in front of the fraction, and then chain rule, I put it in the numerator, in the top. Then it just doesn't take tons of space anymore. And it looks better. You see, it looks much better. Derivative of 8 to the x. Okay, that's exponential function. So you're like, exponential function. I know it copies itself. Copy exponential function. Check the base. The base is not e, so you have to multiply by the natural log of the base. And this is the answer. I would still rewrite the denominator, because 8 to the x squared doesn't look nice. So it's going to be, you can put negative on the top if you want, negative 8 to the x, natural log of x, that came from the chain rule, over a huge square root. I call it huge, but it's not really huge, I don't know, I just like calling it huge. 1 minus 8 to what? X plus 2 or 2x? 2x. Okay, less people hesitating, but still some hesitating. 2x, you multiply the exponents. Yes? Good idea. You can do that too. Oh, interesting. Actually, I did not even think about it. Very good idea. So what he's saying is, can't you just do 2 to the x, and then 8 2 is 64 to the x? I did not think about it. Smart. Yeah, you can do that too. That is 64 to the x. Do you all agree? Because the order can be changed. That doesn't matter. Yeah, good point. I will do or. Both are good. Good job. So that was a good one. And the last one. Let's do one more. Example 3. Example 3. Something with exponential function. Tangent minus 1 of e to the 5x. So we had arcsine, we had arccosine, and now we're having arctangent. Those three usually the one we put on the test. I will tell you. Usually those three we like putting on a test. Arcsine, arccosine, arctangent. That's why I'm showing you those. So y equals this. Y prime. I remember that arctangent doesn't have any square roots. And I remember it's 1 plus input squared. Input squared. Can you check? Can you skip the step and write down input squared right away? E to the what? 10x. Because 5x squared, right? 5x squared. So input squared. And my input is e to the 5x. Something is missing. Times what? Times derivative of the exponential function e to the 5x. The moment you see exponential function, you copy it, e to the 5x, times, now you look inside of the exponent. If there is chain rule, you have to differentiate there a function of the derivative and the exponent. Derivative of 5x is 5, and this is the answer. What do you think? Not too bad? Ask me any questions. But basically, those three are the most important. Sometimes we do a cotangent for homework. But usually, for the test, we know you should know those three. And they are moving to the beginning of the Calculus 2 class. We're going to be drawing them, integrating them, finding solutions for all of this.